So is my screen visible to you? Is the PPT visible? Hello, is the PPT visible? Okay, fine. So I think we can start. So this is our 11th week on key metallurgical engineering live problem solving session. So we had been solving questions from physical metallurgy and mechanical metallurgy for the past 11 weeks, and nowadays we are solving 4 questions per week and plus a few revision questions from the past sessions. So on that note, let me start. And since only two of us are there today, so I will give sufficient time to you and give sufficient hints, and you'll have to try to attempt the questions by yourself, so that it will be kind of a practice session for you. So today's first question is very direct. Which one of the following is an equilibrium defect? Options are vacancies, dislocations, stacking fault, and grain boundaries. This is a 1 mark question that was asked previously. So, which one of the following is an equilibrium defect? So, can you please answer? So, which one of the following is an equilibrium defect? So, we know that there are zero dimensional defects, one dimensional defects, two dimensional defects, and so on. So, out of these, which is an equilibrium defect? It's a basic theoretical question. So, are you familiar with the answer? If not, I'll explain. Vacancies. Okay. So the answer is vacancies. So why do we say that vacancies are equilibrium defects? This is because whenever we are taking a material at a temperature greater than 0 Kelvin, what happens is that a certain number of vacancies will be present inside the material, and the material will be stable. It won't affect its properties. So why do these certain number of vacancies exist? This is because whenever vacancies are present inside a material, actually its Gibbs free energy will reduce. We know that as a stable system is one which has the minimum Gibbs free energy, right? So whenever a material has a sufficient number of vacancies, its Gibbs free energy actually decreases. So why do we say that the Gibbs free energy actually decreases? This is because as the number of vacancies reaches a certain value, the contribution of configurational entropy increases. So if you remember the equation for configurational entropy, it would be S is equal to minus K ln W, right? Where W is the probability of a defect or probability of the state occurring. So as the number of vacancies increasing, there is a probability that these vacancies can switch between themselves, and hence the configurational entropy will increase. That is why we say that equilibrium defects are the lattice defects whose existence is thermodynamically guaranteed at finite non-zero temperature of the lattice, and these are characterized by equilibrium concentration. So the concentration is given by this particular equation. So the concentration of vacancies is given by NV by NT is equal to E raised to minus QFV by RT, where NV is the number of vacancies as a particular temperature T, NT is the total number of lattice size, QFV is the activation energy for a vacancy formation, R is 8.31 joule per mole Kelvin, and T is the temperature. And we can also say that the total free energy of the system decreases as configurational entropy increases compared to enthalpy. So this is based on the Gibbs free energy equation, H minus T delta S. And also, whenever vacancies are present inside a material, it would not affect the macro state properties of the material. Hence, vacancies are equilibrium defects. So the answer is vacancies. So is this particular question clear to you? Yeah. Okay. So we'll move on to the next question. So next is a unit dislocation splits into two partial dislocations. The correct combination of Burgers vectors of the partial dislocation for a given unit dislocation having Burgers vector a by 2 1 bar 0 is. So basically the question is that we know that in order to reduce the distortional energy, a dislocation can split into two other dislocations. So what we have to find is that we have a dislocation, and the Burgess vector of that dislocation is given as a by 2 1 1 bar 0. This particular dislocation splits into two other smaller dislocations, and these are combinations that are possible. From these options, we have to find out which two of the Burgess vector are the ones into which this one splits. So how do we find that out? So first thing is that we know that the elastic strain energy, or the energy that is associated with the dislocation, is given by the equation E is proportional to mu b square by 2. Considering the all other terms constant, we can say that this energy is proportional to b square, right? Hence, we have to b square. B actually denotes the magnitude of the Burgess vector. Therefore, we need to find the value of b. So, the magnitude of a Burgess vector can be obtained by multiplying the lattice parameter to a given vector type. So, what does that mean? For example, a lattice parameter A is given as 2.87 Armstrong, and the magnitude of and Burgess vector type is given 1 by 2 1 1 1. So how to find the value of b? We have to write a into 1 by 2 root of 1 square plus 1 square plus 1 square. Hence the total value will come to 2.485. In our case, we need to find the value of b square. That is because the distortional energy is proportional to b square, and therefore we need to find the value of b square. To obtain the value of b, initially what we have to do, multiply a with the type of Burgess vector. Therefore a into 1 by 2, and whatever term comes inside the bracket, we have to take it as root of 1 square plus 1 square plus 1 square. So that is how we calculate. So, in our question, what we see here, this Burgess vector will split into either these two, these two, these two, or these two. We have to find out. In order to get that, two conditions have to be satisfied. So, what are the two conditions? First condition is that when we are doing the sum of whatever is in this bracket and whatever is in this bracket, it should be equal to this value. That is 2 1 bar 1 plus 1 2 bar 1 bar should be equal to 1 1 bar 0, and we have to check it for all four options. Then only we can say that which options are correct. So that is one method by which we can very quickly solve this question. So that is the first condition. Sum of the vectors should be equivalent. The second condition is that the magnitude of the vectors in the RHS should be less than that in the LHS. So whatever this magnitude is, we have to calculate the b square value for this term, and this b square value should be greater than the b square value of these two combined. So now we'll show that. First, we need to see the equivalence of vectors. So, option A. For example, we are taking A by 6, A by 6, and we are summing up these two. How it will come? 2 plus 1 becomes 3. Again, 1 bar plus 2 bar becomes 3 bar. 1 bar plus 1 becomes 0. Right. Therefore, and when we are taking this 3 common, we can cancel it out, and we can write A by 2, 1, 1 bar 0. This is correct. This is what actually we had in our question. Therefore, initially we can say that the answer to this particular question is option A. Suppose we are facing an issue that all options are giving us the same correct value. Then how do we decide? So before going to that, here also we can check. See, 1 plus 1, we will 1 plus 1 bar, we will get 0. Then 1 bar plus 2 bar will get 3 bar. Again 2 bar plus 2 plus 1 bar, we will get 1. Therefore, this option, and this option will not hold. So, based on the sum equivalence, we can say that option A is the correct answer. Suppose we are finding that all these answers become A by 2 into 1, 1 bar 0. Then what do we do? Then we go for calculating the value of B square. So, for this step, A by 2 into 1, 1 bar 0, B square is calculated as, we have to square this whole term. So, how it will become? A square by 2 square into root of 1 square plus 1 bar square plus 0 square, the whole square, and it will come as a square by 4 into 2. It will become a square by 2. This is the LHS part. So according to the criteria, whenever the dislocation splits into two partial dislocations, whatever energy is associated with the partial dislocation should be less than the energy associated with this term. So for this first term, if we are calculating, how it will become? A square by 36 root of 2 square plus 1 square plus 1 square, that is how much, root of 6 the whole square, therefore it will become 6. When we are can similarly for this term also, a square by 36 into 1 square plus 2 bar square plus 1 square, that is again root 6 the whole square, that also becomes as a square by 36 into 6. Hence, we will get a square by 3. So, when we are comparing LHS and RHS, whenever this particular dislocation split into two smaller dislocation, the energy associated with it got reduced. This is because a square by 2 was the energy. Here, a square by 3 is the energy. That is one another method in which we can verify. Therefore, overall, whenever we are trying to solve this kind of question, we have to do two routes. One is we can either go for the sum of the vectors should be equivalent, or we have to find out sum of magnitude of RHS should be less than the magnitude of the vector in the LHS. Therefore, the answer to this question is option A. So, is that clear? Okay. So, hence the answer is option A. So, yeah, this is the final answer. Now, next is a liquid droplet beta is on a substrate. So, this is some kind of liquid, and whenever the liquid made a contact with some kind of a solid substrate, delta, such kind of a formation or a bubble formation took place. And this medium is air. The contact angle theta is determined using the following expression. So, whenever we have something associated with contact angle, we should remember that it is associated with the Young's equation. So, what is the Young's equation? So, before moving on to Young's equation, can you tell me which of the options will be correct for this particular question? Can you make a guess? If you know the Young's equation, you can directly answer. Option A. Yeah, that's correct. So, how do we tell that it is the Young's equation? So, whenever a liquid droplet is deposited onto a solid surface, it will form a contact angle depending upon the surface tension of the liquid, surface tension of the solid substrate, as well as the surface tension of the interface. So, this is the surface tension of the solid that will be extended to the solid, and when it is extended at these two interfaces, it is gamma SL, and when it is extending through the liquid into the air, it is the surface tension of liquid. And finally, we have the Young's equation as gamma S is equal to gamma L dot cos theta plus gamma SL. So this is referred to as the Young's equation, and this particular theta is known as the contact angle value, and it is a measure of wetting of a liquid. So whether suppose a substrate is there and we have a contact angle value, and if the contact angle value lies between 0 and 90, it is known as a hydrophilic material, and if the contact angle value is between 90 and 150, it is called as an hydrophobic material, and if it is more than 150, what it is known as super hydrophobic with respect to water. So in our case, what are the three? So when we are comparing these two figures, this is gamma S, gamma L, gamma SL. So gamma S is equal to gamma L cos theta plus gamma SL. So here what will be having, gamma A delta is equal to gamma alpha beta cos theta plus gamma beta delta. Therefore, option A will be the correct answer. So, is this explanation clear to you? Okay. So, that is the case. So, next is a material with a grain size of ASTM number 6 has a lattice frictional stress of 100 meganewtons per meter square and locking Hall parameter of 0.10 meganewton per meter power 3 by 2. We have to find the grain size of the material as well as the yield strength of the material. So, before moving on, can you please tell me what is the equation for ASTM grain size as well as the yield strength? Or, like, if you know the Hall pitch equation, that also you can mention. So, can you please tell me what are the equations to be used in this question? One is the Hall pitch equation, one is the ASTM grain size number. So these are the two equations that we use to solve this particular question. Okay, sigma A is equal to sigma A plus K root. That is correct. So what about ASTM grain size? Are you familiar with that part? If not, I will explain, no issues. 2 power n. Actually, it's 2 power n minus 1. Okay, that. So it's a good attempt. So we'll see how to answer this particular question. So here it is given that the material has a grain size of ASTM number 6. So how do we calculate that? So the number of grains, that is capital N, per square inch at 100x magnification is given by the equation that you mentioned. N is equal to 2 power n minus 1. So please note that n is the number of grains per square inch at 100x magnification. Suppose it is at any other magnification. How it will become? N into magnification by 100, the whole square is equal to 2 into n minus 1. In our question, there is no magnification. Therefore, we need to denote the value of m as 1. So, on substituting, we have n is a, the grain size number was 6, right? Therefore, n is a n star 1 by 100 the whole square, 2 power 6 minus 1. Therefore, n is equal to 2 power 5. This is actually 10 power 4. This is not 104. This is 10 power 4. 10 power 4 grains per square inch. So we should note that in our question, whatever they have asked for is grain size, and that too they have asked for the grain size in microns. Here it is given in square inch. It is given number of grains per square inch. From this value, we need to find the size of one grain. So how do we do that? So area of one grain is equal. So there are n number of grains in this much square area, right? Therefore, area of one grain will be what? We have to take 1 by 32 into 10 power 4 square inch. This is also 10 power 4 square inch. So there are n number of grains into in 35 into 10 power 4 square inch. Therefore, the area of one grain is equal to 1 by 32 into 10 power 4 square inch. Now we have to convert the square inch into square meters. So how do we convert square into square meters? 2.54 into 2.54 into 10 power minus 4. First we are converting into centimeter square, and that centimeter square into meter square. And this is square meter. Therefore, on calculating, we'll get the area of one green as 2.016161 into 10 power minus 9 square meter. So, in order to convert the square meter into meter, we have to take the root of this particular value. So when we are taking the root, we will get 4.4901 into 10 power minus 5 meter. That is approximately 45 microns. So the final answer, that is the grain size, is 45 microns. So initially we know that there is no magnification, therefore we substitute the value of m is equal to 1. We got the value of n. Please remember that n is not the grain size. It is the number of grains per square inch. We have to convert this into grain size. So if there are n number of grains per square inch, then area of one grain is equal to 1 by whatever value we obtained. And the square inch has to be converted into square meter. Therefore, we use 2.54, 2.54, 10 power minus 4, and square meter has to be converted into normal meter. Therefore, we will take the root of this particular value. Finally, we will obtain 45 microns. So please go through the steps. So is this particular part clear to you? How to calculate grain size? Yeah. Okay, I'll clear that later maybe. Okay. So next is according to Hall pitch equation, we have to find out, sorry, the yield strength of the material. So as you mentioned, Hall pitch equation is given by sigma y is equal to sigma 0 plus k d power minus zero point 0.5, where sigma y is the yield strength, sigma 0 is the lattice frictional stress, k is the Hall pitch coefficient, and d is the grain size dia. Out of these, sigma 0 is given to us, k is given to us, d we obtained just now, that is 45 microns. On substituting all these values, we will get the value of sigma y. So sigma 0 is given as 100, K is given as 0.10, and D is 45 microns. Please note that 2 are in meters and 1 is in micrometers, and we have to convert it into the same unit. Upon substituting and converting, 100 plus zero point 0.1 into 45 into 10 power minus 6 power minus zero point 0.5. So this particular value will come to 14.905, and when we are converting everything into meter, we will get meganewton per meter square. Therefore, we will be getting 114 megapascal. That is the answer to yield strength. So we have actually answered two 2 mark questions. Before in GATE, they used to ask, like, they would give a single statement, and from that statement they would ask two 2 mark questions, or one mark and one 2 mark, and like that. But recently such questions are not usually observed, but before they used to ask, and this was asked in 2012, I remember. So is this clear to you? Yeah. Okay. So that is the case. So initially we got as 45 microns, and then we got 115 MPa. So that is the case. So this is our revision question for today. This was already solved. So a simplified energy band diagram of an intrinsic semiconductor, a thermal equilibrium, that is 300 Kelvin, is shown. In the accompanying table, which one of the following four columns correctly represents the listed parameters? Assume the same effective mass for electrons and holes. So there are different delta E1 and delta E2, and there are different combinations here. So out of these four options, which of the following one gives the correct definitions? So can you please take 2 minutes and try to answer this question? So this is a revision question. This I have already solved in my previous week. So I just want to make sure that you are well versed with the concept right now. So if possible, please do and try to answer this question. So what is band gap, what is electron affinity, and what is work function? Do you want me to display this question for some time longer? Okay. Yeah. So what is band gap in this? What is the electron affinity? What is the work function? So are you able to answer right now? Okay, sure. So, in case of semiconductors, this will be the particular energy band diagram of a semiconductor. So first we have what is known as the valence band. Inside the valence band, there will be a large number of electrons, and whenever the electrons receive a sufficient amount of energy, they will be excited into the conduction band. Conduction band will be having a lot of empty spaces. The edge of the valence band is known as the VBM, or the valence band maximum. In certain materials, it is also known as highest occupied molecular orbital. So usually for metals and semiconductors, we call them at valence band and conduction band. And whenever the material becomes very small, that is whenever quantum effects start coming, that is when we call them as HOMO and LUMO, where valence band becomes called as HOMO, that is highest occupied molecular orbital, and conduction band becomes called as lowest unoccupied molecular orbital. So between the valence band and conduction band, there will be a region that is devoid of any charge carriers. So this particular region is known as our band gap, and in between the band gap there will be a region known as the Fermi level. So at the Fermi level, there is a 50 percentage possibility of either finding electrons or no electrons. So whenever we are imagining a band diagram, there is nothing like there will be a specific boundary. It is a probabilistic data. We know about electron clouds, right? Therefore, in the middle of the band gap, there is a 50 percentage possibility of finding electrons. So that is what is known as Fermi level. And the distance between the valence band maximum and the conduction band minimum is known as Eg. Okay, some person joined right now. So between valence band maximum and conduction band minimum, we have what is known as the Eg, or the energy gap. And from the Fermi level, that is the 50 percentage probability of finding electron, from the Fermi level towards vacuum, we have what is known as the work function. Again, from conduction band minimum towards vacuum, we have what is known as electron affinity. So what do we mean by this work function, electron affinity, etc.? So whenever that particular amount of energy is given to the material, an electron existing at the Fermi level or an electron existing at the conduction band minimum will be removed. Okay. So EVAC means the vacuum level. EA means electron affinity. Here WF means work function. IE means ionization energy. EG means the band gap. EF means the Fermi level. This is the conduction band minimum or lowest unoccupied molecular orbital. Or we have the valence band maximum or highest occupied molecular orbital. So the highest energy level that an electron can occupy, that absolute zero. So I told that between the conduction band minimum and valence band maximum, there is a region where there is a 50 percentage probability of finding electrons. This is known as a Fermi level. And this Fermi level has yet another definition, that is the highest energy level that an electron can occupy at absolute zero temperature. So beyond that, the electron won't be able to exist. The Fermi level lies between the valence band and conduction band at absolute zero, and electrons are in their lowest energy state. Then the band gap or energy gap is the difference between this particular point and this particular point. An electron can move from the valence band to conduction band only when an energy that is equal to or greater than Eg is supplied to it. Again, work function is a property of a material which is defined as the minimum amount of energy which is required to remove an electron from the Fermi level to infinity. That is, from the surface of the solid to remove it to infinity, we require an energy that is greater than or equal to EF. And the energy level labeled as chi. This electron affinity is usually denoted by the simple chi, and it will be the difference between the bottom of the conduction band to E vacuum. That is the vacuum level. So these are the different sets. Now that we have understood what is Eg, what is work function, and what is electron affinity, we can try to answer our question. So this is the valence band maximum. This is the conduction band minimum. So the difference between these two is delta E1. Therefore, delta E1 will be the band gap. So delta E1 becoming band gap, we have two options, right? Either it can be column 2 or it can be column 4. Next, we have, what do we have? Electron affinity. We know that electron affinity was between delta E2, that is In this figure, if we see, electron affinity is between conduction band minimum to vacuum level. So here it will be from this point till this point. So how do we find that? Delta E2 minus delta E1. Delta E2 minus delta E1 come for column 2. Therefore, we can fix that column 2 is our answer. Just to verify what is meant by work function. Work function means from the Fermi level, that is from 50% probability to vacuum. Therefore, E2 minus delta E1 by 2. E2 minus delta E1 by 2. Therefore, overall we can say that column 2 will give us the correct definition for band gap, electron affinity and work function. So, is this clear to you? Yeah. So, that is all about today. Thank you for your time. And you were asking about test series. As far as I know, like at least, but for the thing is that please consult somebody who has done GATE recently. I took GATE in 2019, and during that time, people used to prefer test series from ACE and MEDC. But now I don't know whether the trend has changed or not. So if not, these you can subscribe by paying a certain amount of money, and you will be able to take a large number of question series from them. And if you're able to solve at least 50% of those questions, surely you will be able to do much better in the actual gate, because the level of hardness for those test series are comparatively very large. So it's better that either you can go for these two test series, or you can consult somebody who has taken metallurgical gate recently. So that is all. Thank you for having me this much time. So thank you so much. Happy New Year in advance. Thank you. You may leave now. Thank you.